Hi everyone, my name is Courtney and I am here with Alana, and in our presentation today we're going to be talking about linear and logistics regression. So here's a little bit about linear regression compared to logistics. It's easier to interpret. It assumes the probability is a linear function of the regressors. It's also faster to compute. It's estimated non-iteratively using ordinary least squares. It requires the dependent variable to be continuous. It uses least square estimation, so the coefficients should be chosen in such a way that it minimizes the sum of the squared distances of each observed response to its fitted value. It requires the error term to be normally distributed, and it can be used to estimate the dependent variable in case of a change in independent variable. So an example of this would be to look at the relationship between the number of hours studied and their grades. And finally, it assumes normal or Gaussian distribution. And just pictured here, you have an example of a linear regression equation, what that kind of looks like, as well as a graphical representation of a straight line linear regression. Alright, so next we're going to look at linear regression and JUMP. Here's just a quick summary of what we'll be doing. We're going to be looking at the big class sample data that is provided in JUMP, and our goal is to see if there's a correlation between height and weight for the 40 individuals who are listed in this data set. Okay, so here's the data in JUMP. There's 40 rows, and the columns include the name of the individual, their age, the sex of the individual, their height, and then their weight. So we're going to analyze, fit y by x. We're going to put the weight as the y and the height as the x, and you can see it's going to choose a bivariate model. Click OK. Here's the plot, and to see what the linear regression will look like, we're just going to do the fit line. So it puts this line in here, and then you can see this equation, which is the equation that it comes up with that's similar to the one that I showed you in the PowerPoint before. Alright, now we're just going to quick look at the results. So this is the summary of fit table, and we're going to look here at this r squared value, and we would like it to be close to 1, and it's really not. So therefore, there doesn't appear to be a strong correlation between height and weight.
So now I will be discussing the logistics regression, or also known as a categorical model. So with this model, it's a little bit more difficult to interpret, but that's also because it's a little bit more complex in the sense of it giving a curved graph instead of a straight line like you saw with the linear regression. It's a little bit slower computation speed because of its complexity. And there are different variables that go into it, just like any model. These would be dependent variables and independent variables. For the dependent variables, you can have more categories, and you can have more than 2 categories. So, as an example of a logistics regression, you could have customers placing an order or not placing an order within the next 6 months. So this would be more of a binomial distribution, and it's only having those 2 different dependent variables. Yes, the customer is going to place an order, or no, the customer is not going to place an order. And the independent variable would be the 6 months, which is a time. So looking into the maximum likelihood estimations, we would want to choose coefficients that are maximizing the probability of y given an x variable. So going into how we're going to do this in JUMP, we decided to use penicillin data. It's a data set that's given, a sample data set given inside of JUMP. Our goal is to predict the probability of a patient being cured. So we're going to go ahead and go over here to JUMP. This is the data that you see when you open up penicillin. So first we look at the dosages that the patient is given and if they have been cured or if they died. And then these are the counts of the patients. And this is the same thing as the dose, but we're adding a natural log value to this. So in graphing it, we're going to go to Analyze, and we're going to go to Fit Model, and this window will pop up, and you would click on Responses, which is being cured or the patient died, this is a nominal variable, so this is your dependent. And we're going to put that in your y, and our independent would be the dosage that you're giving the patient. And we're going to add this down here. So then we're just going to click run, and this graph shows up. So like you saw on the previous slide about the S-curve, this gives the same model instead of a straight line, showing you that there's more complexity in this model than a linear, like I said previously. And we're to see the correlation with the independence of the variables, we're going to go down here and look at the p-value. So with a chi-squared model, you would look at your null hypothesis, which would be that there is independence of the variables that you're using. But since this p-value is so low, that means that there is dependence, which means there's correlation with the variables that we used, which is the dosage and also the, what did we use? The dosage and the response of the different patients. So now we're going to go to the next slide. Actually, as the results said before, there is significance in the dosage and the survival rate of the patients. So to conclude, we're going to show some differences between the two data sets. And for the multiple regression, it's a continuous data set. So as Courtney has showed earlier, with the continuous data set, like where you have two different variables, the dependent and the independent, and they're both continuous. And for the multi-nominal, this would be, again, the logistics regression. It's also known as a logistics regression, and it's categorical. So the dependent variables would be nominal, so it's putting it into different categories again. And for the independent, it can be continuous, ordinal, or nominal. And thank you for watching our video. We hope this gave you some insight on linear and logistics models.